Let's understand how computers solve Sudoku and mazes with backtracking. Imagine a Sudoku puzzle. You pick an empty cell and try the number 5. You check the row, the column, the 3x3 box. No conflicts, so you move to the next cell. You try 3. Wait, now that breaks the rules in the column. So you erase the 3, try 4 instead. Still doesn't work. You erase again, try 6. Valid. You keep going, filling cells one by one. But then, 10 moves later, you realize there's no valid number left for a cell. Something earlier must be wrong. So, you backtrack. You erase your last few choices, return to a decision you made earlier, and try a different number. This is backtracking. A computer does the same thing, but systematically. It tries a number, checks if it's valid, and if it leads to a dead end, it undoes that choice and tries the next option. It never forgets where it was, and it never re-explores a path it already knows is broken. That's why a computer can solve a Sudoku in seconds, while you might take minutes. It's not smarter, it's just more systematic. Backtracking is trial and error, with memory and discipline. Let's visualize backtracking as a tree of decisions. Every time you have a choice, like which number to place in a Sudoku cell, you're standing at a fork in the road. Each path represents a different option. You walk down one path. If it leads to a solution, great. If it hits a dead end, you step back to the fork and try a different path. The key insight is this. You never re-explore a path you've already walked down and found to be blocked. That's the tree structure. The root is your starting state, an empty Sudoku grid. Each branch is a choice. Place a 5 here, or a 6, or a 7. As you go deeper into the tree, more cells get filled. Some branches lead to valid partial solutions, so you keep going. Others violate the rules, so you prune them, cut them off, and backtrack to the last valid decision point. The tree grows left to right in our visualization. Valid choices extend the path. Invalid choices get marked red and collapse. A cursor walks down the tree, and when it hits a dead end, it rewinds to the last fork and tries a new branch. This is the mental model. Backtracking is depth-first exploration with pruning. You go as deep as possible, and only when you're stuck do you step back. As the algorithm explores deeper, it's essentially performing a depth-first search. It keeps pushing forward, making choices and filling cells. The Sudoku grid on the side visually confirms each step, showing how these choices build toward a solution. This constant validation and updating is crucial to ensure we're building a correct and valid path. But sometimes, a path leads to a dead end, a state where no valid moves can be made. This is where the backtracking truly shines. The algorithm recognizes this dead end, marks the path as invalid, and efficiently retracts its steps, erasing the invalid choices until it reaches the last decision point where other options still exist. This is the power of backtracking. Instead of starting over completely, it intelligently revisits prior decision points. It remembers which paths have been explored and found invalid, avoiding redundant work. The tree itself becomes a persistent record, showing us exactly which decisions led to dead ends and which remain unexplored, guiding the search efficiently. By methodically exploring and pruning, the backtracking algorithm guarantees that if a solution exists, it will find it. This systematic process ensures efficiency, as it only explores promising paths and quickly abandons those that lead nowhere. The final green path represents the sequence of valid decisions that lead to a complete and correct solution, a testament to the power of structured problem solving. Now let's break down the mechanics. Backtracking has 3 core steps: choose, validate, and undo. Before you make a choice, you save the current state. Think of it as taking a snapshot. Then you make the choice. Place a number in a cell. Next, you validate. Does this choice violate any constraints? If yes, you restore the snapshot and try the next option. If no, you move deeper and repeat. This state saving is critical. Without it, you'd have to rebuild the entire puzzle from scratch every time you undo a choice, which is expensive. Instead, you just rewind to the last saved state. Let's see this in action. On the left, we have a Sudoku grid. On the right, a stack that stores snapshots of the grid state. Before placing a number, we push the current grid onto the stack. We place a 5. We validate green check mark. It's valid. We move to the next cell and repeat. We place a 3. Validate. Red X. Invalid. Immediately, we pop the last snapshot from the stack and restore the grid to that state. The 3 disappears. We try 4. Validate, still invalid. Pop again, restore. Try 6, green check mark. We save the new state and continue. This loop save, try, validate, restore if needed is the heartbeat of backtracking. It's what makes the algorithm efficient and systematic. Backtracking isn't just for Sudoku. It's a universal pattern for solving constraint problems. Let's apply the same logic to a maze. You start at the entrance and want to reach the exit. You pick a direction, say, up. You move one step. Is this a wall? No. So you continue. You move up again. Wall? No. You keep going. Now, you hit a wall. Dead end. So you backtrack. You step back to the last intersection where you had a choice, and you try a different direction, right this time. You move right? Valid. You continue. Again, you hit a dead end. Backtrack to the previous intersection. Try down. Valid. Keep going. Eventually, you reach the exit. The logic is identical to Sudoku. Try a path, validate it, and if it fails, undo and try another. The decision tree is the same. Each intersection is a choice point. Each direction is a branch. Dead ends are pruned. The same 3-step loop save state, try, validate, undo, applies here too. This is why backtracking is so powerful. Once you understand the pattern, you can apply it to mazes, n-queens, scheduling problems, graph coloring, and more. The structure stays the same. Only the constraints and choices change.